I'd like to welcome to the stage Craig McNeile. He is a lecturer at Plymouth University, so this is his home turf. So, yeah, so I'll let you take the floor. Thank you very much, Craig.
Okay, thank you. Okay, so what I'm going to talk about is I'm going to give you a brief overview of the aims of particle physics. Then I'm going to tell you about a calculation that I'm doing, which is kind of relevant to particle physics. And then the digital part of this talk is going to be the use of high-performance computing to do this particle physics calculation and give you background of some of the kind of high-performance computers we have in the, at Plymouth and around the UK. Okay, so what is the aim of particle physics? It's the ambitious aim of to understand the fundamental particles and interactions between them. And ideally what we want to do, we want to write the equations that explain the entire universe on a T-shirt. And as time goes on, we learn more and more about the universe. So in the past, people didn't know about atoms. Then we found out atoms are made of protons and electrons. And in the past, people thought the proton was a fundamental particle. But it turns out a modern understanding is protons made of 3 quarks and gluons interacting between them. And actually, we have a theory and we can actually calculate the mass of the proton. And now we want to move on. Go deeper and deeper. We want to know, can we compute the masses of the quarks? Can we understand them? And there's various questions that are bound up to the fate of the universe. Okay, so here's my little picture of the proton with the 2 quarks, and these little squiggly lines are the gluons between them. So the world is described by something known as a standard model of particle physics, and this describes all the interactions. One of the things we liked in the 19th century, electricity, magnetism, and radiation, radioactivity, were different things. But nowadays, as we learn more about the universe, they're all unified into one theory. We have theories of the strong interactions and gravity. So we want to understand as much stuff as possible and kind of unify them all together. And a couple of years ago, the standard model of particle physics was completed by the discovery of the Higgs boson. Okay, so I should say down there, this particle physics has been well tested in experiments, and it agrees at the sort of percentage level with data, experimental data. So that's sort of the good news. The sort of the bad news is there's a lot of stuff we don't understand in the universe. What this is a rotation curve. So here's the little galaxy down the bottom, and then here's the distance out from the galaxy. So what they do is here's the velocity of stars going around this galaxy, which they can determine by some kind of Doppler effect. The same thing, similar to the way you the police use to detect the speed of cars. And so you can see the amount of matter there, and then you can do the empirical observation, and this is this green curve. And then if you do the theory, like the way you can solve for the trajectories of the planets, use Newton's laws and the dynamics, and you get a prediction of this curve here. And the fact that they're very different suggests to people that there's a lot of unknown matter in the universe. And so what people think is actually, here's our luminous light, but there's actually a lot of what's known as dark matter. And there's various issues with that. And so as particle physics, we like to know what this dark matter is, or at least explain why these 2 curves are different. And even worse than that, so people have done more experiments, they can also look around. We're bathed in the photons from the Big Bang. This has a temperature around 3 Kelvin, sort of minus 270 degrees centigrade. And when people do specialized measurements of that, it turns out this is also consistent with this idea of dark matter, that we don't understand 25% of the universe. There's also something called dark energy, which is, it's just, we've sort of given up on completely. And we only understand 5% of the universe. So we're great, but we understand 5% of the universe. So our goal is to try and figure out at least what this dark matter is. So there's this thing in CERN, the Large Hadron Collider. This is the place that they found the Higgs boson. And this is the picture, oops, in Geneva. It's a large circular thing, 27 kilometers. And essentially, you're just bashing protons together. They circulate around, And what you're hoping, when they collide, you can create new matter using E equals mc squared. You bash these things together at high energy, and hopefully you'll find some new particle. And this new particle could be from some theory that might explain this dark matter. So that's the kind of hope. This is actually, a proton is actually quite a messy thing. So here's a little thing. This is one of their pictures of a collision. And this happens every few microseconds, whatever level. And these pictures are quite messy because protons are complicated and all a bunch of stuff rushes out everywhere. And you're trying to find some of the stuff here, these lines, are from physics we understand. And we're looking for some kind of line with some particle which we don't know, which will give somebody a Nobel Prize in this mess. So people are using kind of machine learning to try and look at this. And even the theorists now are sort of writing papers with machine learning in this titles. Okay, so fine. Unfortunately, so far, they've not really found any new particles or interactions. And this just could be, because the scale of new physics just could be higher than energy than the LHC can determine. Okay, but there's another way to look for these particles, and this is to... okay, so this experiment, we're looking at the particle called a muon. There's an electron, and then there's a sort of a heavier copy of that, which is 200 times as massive, and it's called the muon. And we don't know why. When it was first discovered, somebody said, well, who ordered that? We don't know why it's there, but it is. And so people do experiments on that, and one of the things you can do experiments with is to look at the interaction with the magnetic fields. And one of the things that people like about this is virtual particles also compute to this measurement. This A mu is the parameter that goes the interaction of this particle with the magnetic field. And what virtual particles just means is, from the uncertainty principle, you can have energy violated for small lengths of time. And that means you can have very, very heavy particles contribute to the properties of this A mu, this muon, which you then can measure. Okay, so here there's a little photon. You have this by muon, and it's a little photon. And the hope is that by making precise measurements of this quantity, you can find evidence for particles that we don't know, and tell us also what the matters of these particles are. Okay, so the way this works is they measured experimentally this number, and then you can do the calculation in a theory. And a couple of things to note about these numbers. The 10 to the minus 11 means the theory and the experiment agree very well, maybe with 10 digits, 10 significant figures, but there is a little deviation. This 10 to the minus 11 is 0 and 11 zeros and 1 1. It's a very small number. And there's a little deviation. These things are little error bars, little errors. And one of these errors, this comes from the experiment, and there's also some little errors from the theory. And so it could be, okay, so this is when it comes down to statistics. It's like we do some statistical experiment, there's some kind of randomness in the experiment, there's some kind of randomness in the theory, and then you have to decide whether it's a significant effect. And this 3.6 deviation, this is very much like you've done statistics, like a 95% confidence level. And you can have various probabilities of whether it's just an accident, like some fluctuations in some of the numbers. And this 3.6 sigma means it's unlikely, but the sigma is just this sort of error bar. And the key number is that once it hits 5 sigma, then somebody gets a Nobel Prize, because then it's just not just a fluctuation, it's some kind of real effect. So where do we come in? Well, some people, because it's physics, not all statistics, some of these interactions here can affect this number, the properties of strongly interacting theory, QCD, and people just don't think these calculations are reliable. And they're taken from data. So people would like a more accurate calculation just to check that this standard model theory could just be wrong because somehow this calculation here is not accurate. Okay, and there's some pressure to do that because there's going to be a new experiment in Fermilab to relook at the experimental numbers. So it's kind of good if you have the theory done before the new experiment comes out. Okay, so what we're trying to do, so there's this calculation that involves strongly interacting particles. So this is what we do. Some of us do at Plymouth, there's a group of 4 of us in the mathematics department. So the strongly interacting theory is called QCD. Quantum field theory means it's quantum mechanics and particles can be created and destroyed. There's a lattice, we discretize space and time, and we put the quarks and gluons on. The way the theory is solved, there's a big Monte Carlo process, and the only equation I have really in this thing is the dynamics of the quarks is determined by a matrix equation that says mx equals b, essentially what is solved for x given b and m comes to the theory. The matrix is very large, just means there's lots of stuff in it, and that means we have to use high performance computing to do this. And when I say very large, the smallest we do is of the order of like 1 million. And then also we want to determine we don't want the lattice. Obviously the lattice is not a real thing, so we have to check that our lattice size is not an error in our calculation. We have to do bigger and bigger volumes. Okay, so this is the more digital part. So we have these big equations. We can't solve them on just one PC, and we solve them on parallel computers. Various people use them around the world, either CPUs or GPUs, and use message passing to do that. Just this application on parallel computers is kind of hard. This application does work well naturally with parallel computers, so we do run certain applications with a lot of cores, and data sets are above 20 terabytes. So I have somebody sent me some data, which is not typical, of running a program on 8,000 cores from a supercomputer center in the US. There's a cascade of computer programs we use to do this. I mean, there's various things. There's the most computation intensive is doing what we call snapshots of the vacuum, and these are really kind of hardcore production level codes which are written in C and C++. But because there's this kind of Monte Carlo process, we're also doing things like statistics and those kind of language down the bottom, which is where most of the physics is done. They're written in R, C, and C++. Because this is a kind of demanding application that can run for years and years, a big calculation, I would say, if you're starting to scratch, would take 5 years. Efficiency of the code is important. So I have a figure here, which I put out a grant application, it wasn't done by me, 38%. So if you have a computer, there's a clock speed, and you know the number of operations done by the cycle in the computer, you can work out what the efficiency is, and then you can time your code to see how close it is. And a lot of applications, 38% is doing really good. And there are some people, not me, I might add, who spend their life just tuning their codes, because also, when we see the cost of these things, a big American supercomputer can cost $100 million. And so if you say, well, my code's only 5% efficiency, they can go, well, why can't we give you $50 million? Okay, so we have a small cluster of computers at Plymouth University for developing projects. This is one of the cabinets. Actually, the building is over in the Smeaton building, actually over in that direction. The bulk of the users of the marine science, as well as School of Computing, Electronics and Mathematics, and the bulk of the users, well, half the users are particle physics. And it was started in 2009. So the kind of kit we had, so we have an older cluster, which is 20 nodes with fast switches, and it's heterogeneous. We've just introduced, getting ready to open up to the people in the university, a slightly bigger, well, a bigger system, fast system with more nodes and more cores and faster interconnects. Because if you're doing parallel computing, the sort of communication between the little nodes, cores, makes a difference to how well your application scales to the number of nodes. We also use this for final year projects, undergraduates as teaching. We just recently introduced a new degree, Mathematics with High Performance Computing, and this is the first time a small subset of the students on this learn the Python programming language, whereas the rest of the students learn mostly MATLAB and R. Okay, so around the UK, there are bigger resources that we also have access to by writing grants. There's something called DIRAC, which is distributed research using advanced computing. And this is essentially now, I think, 4 or 5 facilities situated around the UK, specifically for research into particle physics and astronomy. So what the astronomers try and do, they try and put in dark matter and look at the distribution of stars in the galaxy. And so we use, I use the machine mostly at Cambridge, which has a lot of cores, and there's ones at Edinburgh. There are also machines that have either huge storage or other machines that have bigger memory, because different applications have different requirements. If you wanted the amount of funding that's involved, so 2009 was about 12 million, 2013 about 15 million, and there's been a refresh of some of the systems, so some of these things are getting updated, and yeah. Okay, so although the actual type of the PC computers I'm using changed, the actual environment has changed very little since the early 90s, apart from some very specialized machines. They have a similar environment. It runs Linux, and there's some kind of batch queue system where you submit your jobs, and there's some kind of compilation system. What I'm kind of aware of is a lot of people in the industry are using kind of Amazon Web Services or Microsoft Azure, and we do, when people write proposals for these things, it is much cheaper to build our own kit than to buy stuff from Amazon. And people are now, because we're under pressure to do this, people are actually doing pilot studies to see whether any of the applications in Dirac can actually be run on these things, because even though they have parallel computers, they may not have enough. They may not just scale up for some of our applications. And also trying to investigate the use of OpenStack, so you'd have, so this would be add a kind of cloud-like interface to some of our supercomputers, so you can move between the Dirac stuff to Amazon seamlessly, if it all works out. Okay, so particle physics is in a kind of strange situation. We understand 5% of the universe very well. The rest of the 95%, well, we're working on it, but some people are so optimistic. So sometimes you see in the press this thing called the multiverse. This is where there's an infinite number of universes, each with different parameters. Jesus, I mean, what can I say? I can't say anything positive about that at all. So I'd say some of these people are just sort of given up, really. So what I'm spending my time doing is doing these precision calculations may give us some insight, give us a little hint to what new particles are, and then slowly from that one hint we can build up a better theory. I have down at the bottom some of the stuff for impact. When we get these big computers, the government's sort of saying we should be, or we're saying we're going to drive the economy. So some of them are available for industry partners if they so wish, but there's no like price list, because also we're not offering a commercial system. So yeah, so particle physics is great, so we'll either find out what 95% of the universe is, or we won't. Okay, thank you.